Welcome to the third Introduction to Real Analysis lecture. The topics that we will explore in this lecture include set operations and relations. Okay, so we'll start with the exercises from the previous lecture. So first, let's consider the conjecture. If x is equal to its square, then either x is equal to 0 or x is equal to 1. So we'll prove this conjecture, and the technique that we will use is going to be the alternate proof by cases. And so we will assume both that the hypothesis is true and the negation of one of the cases of the conclusion is false. So in particular, we will suppose that x is equal to its square and x is not equal to 0. Then we can divide both sides of the equation by the non-zero element x, and so we have x divided by x is equal to x squared divided by x, or x is equal to 1, which is another case of the conclusion. And therefore, we have demonstrated that if x is equal to its square, then either x is 0 or x is 1. Now we can prove a stronger statement. Let's consider the converse. The converse is the statement that if x is 0 or x is 1, then x is equal to its square. So proof. Suppose that x is 0, then since 0 is equal to 0 times 0, which is 0 squared, we have x is equal to x squared. So now suppose that x is equal to 1. Then, since 1 is equal to 1 times 1, which is 1 squared, we have x is equal to x squared. And so we have demonstrated that if x is 0 or x is 1, then x is equal to its square. And so we have proved a biconditional, which is a much stronger statement. So we have that a number x is equal to its square if and only if x is equal to 0 or x is equal to 1. Or another way to state this is that a number x is equal to its square precisely when x is equal to 0 or x is equal to 1. So next, let's consider the statement P of x, which is the statement that for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and c is a positive number less than delta, then this implies that the distance between f of x and L is less than epsilon. So recall that the negation of a universal quantifier involves an existential quantifier, and the negation of an existential quantifier involves a universal quantifier, and the negation of an implication is the statement that the hypothesis is true and the conclusion is false. And so altogether, the negation of the statement P of x is the statement that there exists an epsilon greater than 0, such that for every delta greater than 0, we have that the distance between x and c is a positive number less than delta, but, and at the same time, the distance between f of x and L is greater than or equal to epsilon. Okay, so new definition. For a given mathematical system, the universal set is the set of all elements under consideration in that system. Now, this definition may seem vague, but we can make it more concrete by specifying which mathematical system we mean. But generally, for mathematical systems, in real analysis, the universal set is generally the set R of all real numbers. Okay, so let's look at a new axiom. And this is known as the axiom of separation. Let X be a set, a sentence f of y for which f of y is a statement for all elements y in the set X. There exists a set, which is the set of all those elements y in the set X, such that the statement f of y is true. So this axiom tells us that for a given universal set, we can generate subsets of the universal set using specific properties or conditions. And so these are subsets of the form all the elements X in the universal set such that a statement f of X is true. So let's use this axiom to define some new sets. Let A and B be subsets of a universal set U then the union of A and B, which is denoted this way, A union B, the intersection of A and B, which is denoted this way, A intersect B, and the complement of the set B in the set A, which is denoted this way, A backslash B, and this is read A set minus B. These sets are given by the union of A and B is defined to be the set of all elements X in some universal set such that X is in the set A or X is in the set B. The intersection of A and B is defined to be the set of all those elements X in a universal set such that X is in the set A and X is simultaneously in the set B. And the complement of the set B in the set A is the set of all the elements X in a universal set such that X is in the set A and X is not in the set B. And if the intersection of A and B is the empty set, then the sets A and B are disjoint. Okay, so we've just had a blast of new definitions. So let's consider how these definitions relate to the logical statements that we've been looking at in the previous lectures. So let's consider what it means for an element to be in the union of A and B. We know the definition, and we can see that this is equivalent to the logical statement X is an element of A or X is an element of B. So now we consider what does it mean for X to not be in a union of A and B? Well, this is equivalent to the negation of this statement. And so we had not, it's not true that X is an element of A, and it is not true that X is an element of B. And so if an element X is not in the union of A and B, then that means that the element X is not in the set A and that element is not in the set B. So now let's look at what it means for an element to be in the intersection of A and B. This is logically equivalent to the statement X is an element of A and X is an element of B. And so what does it mean if we say that X is not an element in the intersection of A and B? We take the negation of this statement, and so we have not, or it is not true that X is an element of A, or it is not true that X is an element of B. And so if X is not in the intersection of A and B, then that means that X is either not in the set A or X is not in the set B. So now let's look at what it means for an element to be in the complement of the set B and the set A. This is equivalent to the logical statement X is an element of A, and it is not true that X is an element of B. And so what does it mean for an element to not be in the complement of B in the set A? We take the negation of this statement. The negation of this statement is the statement that not, or it is not true, that X is an element of A, or a double negation, it is true that X is in the set B. And so if an element X is not in the complement of a set B in the set A, then that means that X is not in the set A, or X is in the set B.